and build their own building using the prescriptive requirements set out in Part 9. And unfortunately, as a structural engineer, there's more to it, and so there are a lot of assumptions in the way Part 9 is written that are quite easily, it's quite easy to go beyond those requirements in almost any building. And so it's a fine line of knowing when to start asking a structural engineer for some support and some answers to some questions. So we're going to go through today, focusing at the start, we're going to look at section 9.4, which talks about the general structural requirements. And then we're going to go through in order, following that, looking at soils. We're going to look at footings, foundations. We're going to jump ahead to talk about columns. And then we're going to spend most of the time today on 9.23, which is wood frame construction. And the nice thing is, if you have a copy of the new National Building Code for Part 9, all of the appendices and notes related to these sections are all within one volume now. So we have the standard up at the front and then the notes at the end. Nice, perhaps, in a future version for those notes to be side by side with the clauses and the provisions the way we've seen in some of the other codes in other countries, so that you get the notes as you're reading along. So let's get started. So structural requirements, we're just looking at section 941 right at the start, which really defines what we can do using Part 9. I just remind everybody to please mute their mics if you could. So the first provision is that any structure has to meet any of the following three requirements. The first is that either it meets Part 9 of the code, or that it meets the engineering guide for wood frame construction. And this guide was put out a few years ago by the Canadian Wood Council. I've got an image of it for you here. Because we realized that there were a lot of instances where building components fell somewhere in this gray zone between Part 9 requirements and Part 4 requirements in the structural section of the building code. And the concern here was that we were, sorry, I've got a note here. You're seeing part of the intro slide. Can you see the image of the cover, Kristen? Can you just confirm that for me, please? Yes, you see the cover, so that's fine. As long as you can see the cover, you can I think you actually have to buy this guide. What's great about it is it fills this gray zone where buildings that kind of fell somewhere in this area. We weren't quite sure how to design it, and then we'd get in arguments over whether or not engineering was required, and the engineers didn't want to sign off on things. They couldn't sign off an entire building. So this is a second option for us, which didn't exist until recently. And then the third option would be full structural design under Part 4 of the building code. Quite often in a Part 9 building, I've got some noise online. Could everybody please make sure their microphones are muted? So if your building meets any of these three requirements, then that's great. Even a Part 9 building may have some components that fit under Part 4, and an engineer would be required. I'm sorry, I have a note here from Kristen. I'm going to try to, I don't know what's causing that. So, specified loads, section 9.4.1.1 There are different types of loads that engineers look at. There's dead load and there's live load. And live load due to occupancy is spelled out in the code, and we'll talk about that momentarily. But other loads are not controlled by people. These are controlled by nature. And so we have site-specific design loads that are defined in the code for snow loading, for wind loads, rain loads, and seismic loads. And all of those are found in Appendix D, these tables which spell out the names of every city and the climatic data associated with each city. And those are still important even under Part 9 design, as you'll see in a moment. The first one, looking at specified loads for snow. Minimum snow loads are determined by this formula. So S means the specified snow load, and that's the load that we're going to be using when we look at span tables. But to get that value, we have to take the values that are provided in the appendix climatic data and multiply them using this formula. So CB is called the basic snow load factor. SB is the basic snow, or it should be SS actually. And SR is a load due to rain accumulation. So there's a combination of snow and potentially rain. So you have a combination of wet snow that's accounted for using this formula. And in no case should this amount be any less than 1 kPa. So here's an example, and if you look on the top right, there's an example of a house with a fair amount of snow. That one is in Whistler, BC. Very dense snowpack. They get a very wet snow, so the factors for that location are going to be very specific. One of the interesting things in our building code when it comes to snow is historically in Canada, the failures that have been observed on roofs due to snow are typically in Part 4 buildings, and not necessarily in Part 9 buildings. And so statistically, the writers of the code have looked back and said, well, typically Part 9 buildings, they have a lot of repetitive members, they're closely spaced, the buildings are only a certain size, the effects of additional snow drifting, even the effects of snow, we just haven't seen the types of failures or the number of failures due to snow. So because it's less common, they've reduced the basic factor. So CB, the basic load factor, in Part 4 design is 0.8. So it's about double, almost double, the factors that we'd use for designing a house or a small Part 9 building. So CB is 0.45 when the width of the roof is less than 4.3 meters. And for larger roofs, it's 0.55. And there is a limit because anything larger than the Part 9 prescribed limit automatically falls under Part 4, in which case CB would be 0.8. So for today, you don't have to remember 0.8. Just be aware that when an engineer designs a Part 4 building, the snow loads are going to be higher. So this is how we determine the snow. So let's look at an example. I'm in Toronto, so we've got a Toronto-centric location picked for today. Toronto, North York. The width of the roof is more than 4.3 meters. So we're going to look at Appendix C, Table C2. And from that table, and I'll show you a slide in a moment, from that table, SS is 1.2 kPa. And SR, due to rain, is 0.4 kPa. Let's look at the table. So this is one page of the table, and right down here in the middle, there's where the red arrow is near the top. That's the column for snow load, and it's a return period of 1 in 50 years. So the building code is calibrated to a return period of 1 in 50 years for snow. And near the bottom, for North York, S sub S is 1.2 kPa, and S sub R is 0.4 kPa. So let's put that in the formula. We take S, it's equal to 0.55 times 1.2 kPa. So 0.55 our CV factor, because the problem stated that the roof is greater than 4.3 meters wide. And we add 0.4 kPa, and that gives us 1.06 kPa. And that value is greater than the code minimum of 1.0 kPa. So we'll use 1.06 for designing. And now we can use that number and go into the span tables and design the roof members for that load. We're not going to do that right now, but we'll do that a little bit later. There are some other cases where we do need to think about snow and occupancy happening at the same time. And a good example of this is exterior decks and balconies, because they can be subjected not just to snow, but to people being on them. And in Part 9, minimum residential load on a balcony is 1.9 kPa for a live load. And we have to take the greater of the snow load or the live load. We don't have to look at them happening at the same time under Part 9. The 1.9 kPa can be looked up in tables in Part 4 because a balcony or a deck for a different type of occupancy may actually require a higher load. So just be aware of that. But this actually comes from clause 9.4.2.3, and in 9423 it actually says 1.9 kPa. The other area that we need to consider loading is attics. And typically attics are only designed to be an empty space. They're not meant to be used for storage. And so the ceiling joists in an attic are only designed under Part 9 as a prescribed element to resist the weight of the finishes that are hung from it and a little bit of the material from above. So they are designed for a pretty small load of 0.35 kPa, not meant to be used for storage, not meant to have a large enough opening or accessible by a stair, so that it wouldn't encourage people to store anything or start using that space. This is an example of ceiling joists. So the actual roof structure is up above in this photo. The roof rafters are sloped. There's lumber sheathing. This is from a house that's about 100 years old. And then above that lumber sheathing is the roofing. But the ceiling was being held up by ceiling joists. And these joists also help to tie the bottom of the rafters together, which is nice. It creates a stable structure for the roof. But primarily their function is to support the drywall or lap and plaster, as was the case in this building. Section 943 deals with deflections, but it really doesn't say very much. I mean, it has the limits on deflection, the permissible limits. So for example, roof rafters in the first line, if there's no ceiling directly mounted to the roof rafter, so that, like the case we just looked at in that photo, the ceiling would have been attached to the ceiling joist in this case. But the roof rafters themselves don't have ceiling attached to them. So the deflection limit is only 1 over 180, or the length divided by 180. Whereas if it did have plaster attached to it, we'd be concerned with cracking the plaster or the gypsum, and so a tighter deflection limit of L over 160 is provided, the length over 360, sorry. And so on. And so here is a list. Floors, all cases are designed for a deflection limit of 1 over 360. Now the question is, how do you actually check that? Because there is no guidance in the code, and the answer is ask your structural engineer, because they'll have the formulas and they'll understand how to apply the loads and design for that. Or if there's span tables that already account for this that are built in, then you don't really need to think about it. It's going to be part of the design criteria that were used to develop the tables. And those tables are at the end of Part 9. We'll talk about them shortly. Okay, well, I'm going to jump ahead to foundation conditions. This is the next section on page 9-8, clause 9.4.4. And this talks about the subsurface conditions that you're going to bear the foundations of the building upon. So foundation conditions, we need to consider what is the allowable bearing pressure of the soils that we're going to bear on. What happens in cases where we have a mixture of materials, that perhaps there's some weak soil and down below there's some rock? What happens if there's a high water table? What happens if there's soil movement? And how does that affect our building, or what can we do to prevent the movement in the first place? And then finally, let's talk about walls that are supporting earth. So there's a basement wall in a building, for example. The basement is empty, but there's earth pressure up against the wall, and how is that resisted in the building? So foundations and bearing pressure, we have different types of foundation systems that are used for buildings. Probably one of the most common on soil is a spread footing or a shallow footing. So we dig down, get to sound, undisturbed soil that has good capacity, and then we pour some sort of footing directly against that soil. And that can be in the form of a strip footing or an isolated pad footing directly under a column. Section 915 specifically deals with the design of foundations, but there are so many limitations that in many cases we could have to go beyond what's in Part 9 and switch to Part 4, where a structural engineer and a geotechnical engineer become involved. And generally, I would just exercise caution when making decisions about foundations. If you are an architect, use your other consultants to your advantage and don't make assumptions about subsurface conditions. If the soils are really poor, an alternative would be to use a deep foundation, and that means something like a pile or a caisson, like in this photo, or other types of systems. But to design that, that's really beyond Part 9, and that's where a geotechnical engineer gets involved and a structural engineer to design a foundation solution. So the code tells you to go directly to that area of the code. But in spite of that, there is a table, table 9.4.4.1, that provides allowable bearing pressures for various types of soils and rock. And it is interesting to look at, just to get a feel for the difference in capacity of different types of soils. Right down at the bottom of the table is sound rock. So this is bedrock. And the bearing capacity is 500 kPa. And a geotechnical engineer could tell you if perhaps that number could even be greater for certain locations depending on the type of rock. But knowing no more than that, that would be kind of the best case scenario. And at the low end, fourth from the bottom is soft clay, which is down around 40 kPa, and that's really a poor soil. So I know for a lot of people that if they don't have better information or no investigation has been done, no information is available, they'll make an assumption initially of somewhere around 75 or 100 kPa and design on that basis until more information is available. Section 9442, sentence 1, deals with the situation where you might have a weaker soil but then rock down below. And the question is, are you allowed to use that higher capacity because you know the rock is going to be stronger? And the rule is that if the width of the footing that is required for the weaker soil, if you look at that depth, if you make the width equal to the depth, and the bedrock isn't within that depth, then you have to use the capacity of the weaker soil that's up above. And in fact, in my practice, I'd probably just assume that unless I can actually bear directly on the rock, I would just choose the weaker of the two. But that's up to you as a practitioner. Just move on here to the next section in the code. Sorry, I do have a question right now that I think I should answer as we go. What is typically contained in a geotechnical report? And I can tell you that typically the most minimum requirement would be a bearing capacity. So the value in this table is something that we would want to get from the geotechnical engineer. I, for one, I wouldn't know the difference between a soft, a firm, or a stiff clay and all these others. But they're in the practice of defining what those are and doing tests on them to provide good values. And if they do boreholes, they'll be able to tell the makeup of different layers and stratification of the soils down below. They would also be able to tell you the groundwater table location, which can be important, and I'll get to that in just a minute. And they would probably also make a recommendation on the type of foundation to use. So if it would be a pile, a spread footing, any other type of product that might, or type of foundation that might be required. So one of the last items here is the high water table. What happens when we are aware that the water table is pretty close to where our footings are? But if the water table is above our foundations, then we have a problem with hydrostatic uplift on a foundation. But regardless of that, section 9443, article 9443, specifies that if the water table is within a distance below the footing that's equal to the width of the footing, I've got an image I'll show you in just a second. If that water table is within that distance below the footing, the capacity of the soils must be cut in half. So here's an image. So the width of this footing is 500 millimeters in the example. And the water table is shown as being, I'm not sure if you'll be able to see my mouse, but this is meant to be the water table, this dotted line. And that's within 500 millimeters of the depth below the footing. That means we have to consider the water table, and as a result, we will discount the capacity of the soil by 50%. So that's basically doubling the size of our foundation requirement because we're cutting the bearing capacity in half. So let me just say, again, this is a case where the water table is below the foundation. Again, if the water table is above, you do need to have structural design for a floor slab that can help resist that uplift that would be caused by the groundwater. Or to avoid the problem entirely, shift the bottom elevation of the foundations upwards and always build above that water table. And information on that can also be found from the local municipality, any conservation authorities. It's quite common that they would understand where the floodplains are and high groundwater. Soil movement is something that is a concern, and it depends on the types of soils, again, and the code doesn't really give us much information except to say that movement can occur due to moisture, freezing, or chemical and microbiological oxidation. So measures should be taken to reduce those effects. And microbiological systems include things like organic materials, which are never a good idea below a foundation. So when we talk about clearing a site and going to undisturbed soil, we mean soil and not organic materials as well. Finally, in this section 9446, we talk about supporting drained earth. So this is the case where you have a basement wall and there's pressure just due to water that's naturally occurring in the soil, and so we get a hydrostatic pressure against that wall, and we're given a unit weight or density of 480 kilograms per cubic meter. Now, if there's anything else than that outside of the foundation, or if the soil isn't drained, but can actually build up the fluid pressure up against that wall, then it turns into more of a retaining wall, and part 4 starts to take over. So the structural design is required for that wall. Particularly if there's surcharge loading. Surcharge may even be a vehicle driving by. If there's a laneway directly against a building, maybe it's an access route for fire trucks or heavy vehicles, that would be something to consider in the design of that foundation. So we're going to jump ahead now to section 9.15. 9.15 is the actual design of the footings and the foundations. Sorry, I have a question about 9.442. Foundation capacity on weaker soil and rock, so I'll just jump back here. So where the weaker soil exists between below a bearing surface, that's within twice the footing width. And yet there may be a stronger soil down below. So if the soil is sitting on top of rock, but the rock is actually quite deep, we would use the bearing capacity of the soil and not the rock. But once the soil becomes pretty shallow, equal to a distance of the same distance down as the width of the footing, then we could start using the capacity of the rock. That's kind of similar to what's shown in this image, but if you replace the depth of the water table, which is shown as WT, and if that was the rock down below, same thing, except that we would actually be increasing the capacity of soils. Hope that answers that question. So let's talk about footings. Footings are a requirement in all buildings. We have to bear on something, and we want that to be very strong. And by the code, these are the elements that are typically required to have some sort of foundation beneath them. So walls, pilasters, columns, piers, fireplaces, and chimneys. I've got an image here of a heavy stone chimney that has its own foundation, separate from the rest of the house, but yet tied in and tied all together, because that's quite a heavy structure on its own, and we wouldn't want settlement caused by that to start affecting other parts of the building. We already talked about the subsurface conditions. Footings have to rest on undisturbed soil, on rock, or on compacted granular fill. We need good material below the foundations to make sure that we have the capacity we need and that there won't be much displacement or movement over time. And what's interesting with Part 9 is because it's a prescriptive section of the code, it's implied in all of the tables that the buildings are only a certain size, right? Maximum of 3 stories, maximum square footage, maximum area and floor plate. And so on that basis, we have minimum footing widths. So let's look at an example here. I'll just pick single story. Minimum width for a single story wall, the width of the strip footing has to be at least 250 millimeters. That's 10 inches. And that's on an exterior wall. And for an interior wall, the width of that strip footing would only be 200 millimeters, or 8 inches. And if we have a pad footing under a column on the far right here, for columns spaced at 3 meters on center, the area of the pad footing is 0.4 square meters. So the units change. This isn't per millimeter, this is square meters. And 0.4 square meters is equivalent to 630 millimeters. That's a pad that's about 25 inches by 25 inches square. That's for a column. And as the building gets higher, if it's a 2-story building, then the width of that strip footing at the exterior becomes 350 millimeters, And for a 3-story building, it becomes 450 millimeters. And what's interesting is somehow the numbers worked out for a 3-story building where the interior strip footing becomes 500 millimeters and actually exceeds the size of the three-story building. And similarly, a column, assuming it's picking up columns from above that are all in line and just carrying the load straight down to the foundation, we end up with a pad footing of 1 square meter, which is so it's about 3 feet, just over 3 feet by 3 feet squared. Now the wall that sits on top of that foundation strip footing also has a minimum thickness, and so Part 9 has tables which help us determine what the thickness of the wall is. And so table 915.4.2, which is on page 9-95, that table is specific to solid concrete and unreinforced concrete block. And the purpose is to tell you how wide that foundation wall needs to be. So if you have a concrete foundation wall using 15 MPa concrete, maybe it's site mixed, the range of wall thicknesses varies between 150 and 300 millimeters. And for each of those, we need to know what the top, how tall the wall is, and also whether or not the top of that wall is laterally restrained. So lateral restraint in a wall means that the top of the wall isn't just free floating up in the air. It isn't just cantilevered up like a flagpole with nothing else around it. A typical basement wall, where the top of the wall is connected to the floor framing, that would be considered laterally supported. So if you have that table handy, you'll see that there's a laterally supported condition, and the maximum height of the wall, if it's laterally supported, is provided. If it isn't laterally supported, so what's an example of a wall that's not laterally supported? Perhaps a staircase coming down into a basement where there's a concrete wall on one side that's just facing the soil, but there's nothing at the top of the wall structurally to restrain it. That would be unsupported length. So that's for solid concrete, reinforced, or unreinforced concrete block for the foundation wall. The next table in the code, table B, is for laterally supported reinforced concrete block. So we increase the capacity because now we're saying that the concrete block foundation wall is going to be reinforced. And that table has a lot of different options for the amount of reinforcement depending on the height of the wall. And so I didn't bring it up here today, but just be aware that you have to pay quite a bit of attention interpreting these tables. And the third type of foundation wall that's considered by the code, which was a relatively recent addition to the code, was insulated concrete form walls. And so there's another table and a whole section describing insulated concrete forms. That's 915.4.5. And in that table, we're looking at systems like this, where the formwork, rather than being made out of plywood or forming, is actually an insulated form. So it's a block, and in this case, the concrete hasn't been poured yet, but within that wall, there could be reinforcement, and then concrete is poured into the top of the wall. The insulation is left in place permanently, and so we have a nice thermal barrier as well as having the foundation all in one. Couple of notes. 915.4.6 specifies how high a foundation wall must extend above the ground. And 150 is the minimum height above the finished ground level. My understanding of this is it's in place to be able to protect the structure above. So assuming that there could be some extra soil buildup over time around a building, or in the winter that snow would accumulate right up against the building, that if you have wood frame structure above or any cladding type product, it would be raised 150 millimeters and to get it away from that wetness and the soil condition. And in terms of protection as well, joists on masonry walls, typically, if it is a masonry wall, the top course should be filled and made solid, or at least provide a 50 millimeter layer of solid masonry or concrete right at the top of the wall. And the reason for that is to tie the whole wall together and provide a location for anchor bolts to be installed at the top of a wall. So on the left-hand side, you can see a masonry wall that's capped with 50 millimeters of solid masonry. And on the right, instead of just a 50 millimeter cap, the entire top course of masonry is filled with concrete. So that can be done with a bond beam. Reinforcement could be placed in it. And that's assuming that the rest of the masonry wall isn't reinforced or is only partially reinforced and grouted. Another aspect here in section 915.5.5, when we talk about the support of joists or even beams on a wall, beams are a concentrated load, so directly below that beam, we need to have a solid piece of masonry or solid grouted masonry directly below the beam, and then that force, the reaction from that beam gets distributed throughout the wall. And masonry is great because it has this sort of arching action within it so that the force gets distributed at something like a 45-degree angle down into the masonry and starts to engage the entire wall. But you need that almost keystone element that's directly below the I-beam to help distribute that force and resist the reaction. So the requirement is that it's at least a 190 millimeter piece of masonry, which is typical for the masonry anyway. So we're talking about replacing one block of masonry and filling it with a solid piece or concrete. And if the foundation walls are thin, and that we wouldn't normally think of a foundation wall being 140 millimeters or even less in thickness, but if it were the case, then a pilaster would have to be provided under the beam, and basically a localized thickening like a column built into the wall and projecting into the space. So here's an example of why that might happen. So in this case, we have a steel beam in a floor, and it's sitting on top of the masonry foundation wall, but the masonry wall is stepped in, very likely so that brick can be installed on the outside. And so in this case, the wall is now narrower, but locally under that beam, we require a pilaster to be installed. Now, the pilaster minimum size has to project into the space 90 millimeters and should be at least 290 millimeters wide. So that's built up using masonry block, and then it's filled with concrete or grout. And similar to that other example where directly under the I-beam we make sure that there's a solid piece of concrete, same thing applies in this case. And finally, parging and finishing of these walls. Block foundation walls, the portion of the block wall that's below ground level must be parged on the exterior, and that's to help protect the wall and also provide some means of resisting some moisture penetration, although there should be waterproofing on the outside of the foundation as well. Any portion of the block wall above the ground level, it can also be parged, but at a minimum, it should have tooled joints so that the joints are nice and clean and complete without any gaps. And I believe we had a question of how high above grade does the foundation wall have to be as I mentioned, it has to be 150 millimeters above the finished grade. And that's a general requirement that is applied to all buildings, not just in Part 9. Okay, I'm going to skip section 916, which is floors on ground, and jump ahead to columns, section 917. There are a few rules about columns. One is that we want columns to be centrally located on their footings and any piers. So this is an example of a crawl space with a solid sawn post and a built-up wood beam sitting on the post. And it's a bit of an illusion here, but the base connector at the bottom of the column is eccentric to the column itself. In reality, this column is seated correctly. It's centered on this masonry pier, and that pier is centered on a foundation. That it may look like rock, but that's actually just a skim coat of concrete that's been placed on the soils here. The point here is that the column aligns vertically down through the pier and into the footing. If it didn't, we would have an eccentrically loaded footing, which can be a problem because it would start creating some rotation onto the footing. Second aspect about columns, and I've got the same photo here, is that the column itself must be supported to resist any lateral movement. So in this case, because it's connected to the beam above, and that beam is connected to a floor, the top of the column is effectively restrained. And the bottom of the column, if they had put that connector in properly and nailed it in place, the bottom of the column would also be considered supported. Now, technically that's a pin, if you ask any engineer. This is quite a squat column, and there are other elements that are restraining it as well. So typically we want the column base to be as close as possible to the base of the footing and the pier. Steel columns. Steel columns are actually prescribed in 917.3, and a minimum size is provided. We can picture in a lot of Part 9 buildings, if you've been in them, that there's some adjustable posts that are available at almost any hardware store that people buy. If you're inspecting and checking to see what was used, these are the minimum requirements, so 73 millimeter outer diameter and a wall thickness of 4.76 millimeters, which I believe is 3/16 of an inch. So relatively thin wall section. Obviously, columns can come in other shapes and sizes in steel. They can be square, they can be I-shaped or H-shaped. But these are the minimum requirements. Wood columns come in a variety of shapes and sizes. The width of the column must be equal to the width of the member that it's supporting. So on the right-hand side, we see a cross-section through a beam at the top in this image. So that's a 4-ply beam made out of 4 pieces of wood, and the column supporting it has to be at least 4 plies wide to match that column. That's a prescriptive requirement. On the left is a photo showing a build-up of a column for a much heavier load and wider beam as well. The nice thing with studs is you can just keep adding more, but you want to be efficient at the same time. Now, wood columns can also be solid sections, solid wood. The example shown in this photo is actually a glue laminated column, and I've drawn in orange the lines, the glued lines for that column. Glued laminated lumber is manufactured to a CSA standard, so this is not people who think they can just grab a few pieces of 2x6 and glue them together. There's strict rules on the adhesives and method of gluing and the grading of the lumber. So if you see glue laminated timber on a job site and you didn't ask for it, make sure you ask for the paperwork to support its capacity and where it came from. And finally, failing that, if you don't have a solid piece or a glued laminated piece, you can build it up as well just by nailing or bolting together pieces of wood, 2x4s, 2x6s, 2x8s, etc. One other thing to note, wood in direct contact with concrete or masonry or the ground is never a good idea. Wood will absorb moisture, and so the code specifies that if you do have wood in direct contact with concrete, that do not put it in direct contact, provide some sort of membrane. So 917.4 specifies that a thin layer of polyethylene or type S roll roofing be provided below the column. A steel base plate or bracket like the one shown on the right here serves the same purpose because it separated the wood from the concrete. Wood absorbs moisture. Concrete is hydrophobic, so it pushes water away from it, and if the wood is right there, it will be like a sponge and it will start to deteriorate. So if you want to avoid decay, the three things to avoid are, well, the three things that cause decay: you have to have oxygen, you have to have moisture, and you have to have food. And that's what the bugs like to eat. So the wood is the food, and if you can remove, you can't remove the oxygen, but if you can remove the source of moisture, that will preserve the wood. Second last section of 917 speaks about unit masonry columns, so using concrete masonry units to build up columns. And this was quite common 50 to 100 years ago. Most Part 9 buildings, in the basements at least, you could find a line of columns right down the middle of the buildings. And they're just basically a big square built up of masonry units, usually, as you can see here, 290 by 290, which is approximately 12 inches by 12 inches as a minimum, or a rectangular version of the same thing, and the rectangular being useful because if two beams are meeting over column, then there's more bearing surface for the beams. Code does have a minimum requirement for not only the size, but also the type of masonry that's being used. And most masonry in Canada, I would expect, should meet these minimum requirements and be made in accordance with CSA A165.1, capacity of the masonry of 15 MPa. So that's a minimum requirement. The columns can be grouted solid. In some cases, there may be rebar as well as part of reinforcement in the column. And finally, columns can also be made out of solid concrete, and the code provides minimums. I would expect that the design of these columns would actually be done by a structural engineer, and there would be reinforcing in accordance with Part 4 of the building code. Minimum size is 200 by 200, which is 8 inches by 8 inches, or 230 millimeters diameter, because forming a circular column using a sonotube is actually quite easy. Cardboard sonotubes are readily available, and concrete can be poured into them. Okay, we're making good time. Now moving on to, sorry, I see there's a question on built-up columns and another question on glulam and that photo I showed. So let me answer this question on wood columns. The question was just, can I provide more explanation on built-up columns? So a built-up column is a way of trying to make use of conventional stick frame lumber. So if you have some 2x6s on a job site, if you nail them together, you can build them into a larger section rather than paying for a solid piece of 6x6 or 8x8. But there are rules about how we connect the pieces to each other. and there's a minimum nailing pattern that's specified in Part 9 to connect those pieces to each other. And most carpenters, when they're trained, learn how to nail them together. There is an option as well to bolt them together. And under the Wood Engineering Design Code, CSA 086, capacities are given, and they're different depending on whether they're nailed or bolted together. But it's a very efficient way of using sawn lumber and individual 2x material. Now, when studs are built up within a wall, the load capacity is different than if it's considered an isolated post in the middle of a space. And the reason for that is in a wall, there's sheathing on the wall that's nailed to the column, which provides additional restraint in one direction. And so if you have an isolated post in the middle of a building, it's not restrained by plywood or OSB sheathing, and it can buckle out in any other direction. So the design of those is slightly different from an engineering point of view. Glue laminated columns, I think the question was specific to this photo. Was it okay that the column was overhanging the concrete support? And good question, good that you noticed it. And yes, it was something that had to be reviewed. So no, it was not okay. It had to be reviewed, and in the case here, it worked out and it was okay. Another question is about what is the class of timber that's suitable for structural elements, and I'm going to get into that in a moment as we talk about section 9.23, wood frame construction. Just jump ahead. So wood frame construction, what's interesting is in Canada and the United States, 90% of our houses for single-family homes are wood frame construction, and they fit well within the Part 9 section of our building code. And as a result, we have all these prescriptive rules because we want to make housing accessible to everybody. And historically, I think it actually dates back to the Chicago fire around the 1870s or so, when right after the fire, there were these books of like recipes for building a house. So it was like a single page that had an image of a 1 or 2 story house and a shopping list of all the parts that you needed to buy so that you could build it yourself, because the government needed to get people housed really fast, and so that was a way of making it accessible to everybody. So the United States, their building codes evolved, and so did Canada's, in a way to make Part 9 type buildings readily accessible in wood frame. And the way we build in wood has actually changed over time. Initially, the 2-story building would have been built in what we call balloon framing, where the walls are made out of studs that are continuous from the foundation right up to the roof. So a single stud that goes right from the foundation and up to the roof. And then the floors are hung off of the studs. So there's a floor plate, it gets into the stud, and then there's a small ledger that the joists can sit on. So that's what's called balloon framing. Platform framing is more of the quote-unquote modern way of doing things. We've been doing it for probably about 50 years now. And in that scenario, we build the walls, a single wall for the first floor, then we bear the next floor on top of that wall, then we build the next wall, and then the roof sits on top of that. And that's called platform because we use the first floor as a platform to build the stud wall, and then we tilt it up into position, put the next floor on, and use that floor as a platform to build the next wall, and then tilt it up. So those are the 2 different methods. And in here, you can see a lot of different components. So if we look a little closer, the vertical elements are studs. There are horizontal pieces which are blocking. This wall has a lot of blocking in it, which we may or may not get to today, but not necessarily a Part 9 requirement. And at the bottom, there's what's called a sill plate. So it's a horizontal piece, which is the same size as the stud material. So if these are 2x6 studs vertically, that plate would also be a 2x6. And at the top of the wall, there's another 2x6 plate, but it's actually doubled. There have to be 2 plates at the top of the wall and a single plate at the bottom of the wall. Now, because this is a prescriptive section of the code, implied within the code are limits on how big the building is. Because if we went beyond those limits, then all tables wouldn't be valid anymore. So one of the limits is that the total structure span is 12.2 meters, and that the walls themselves are not foundations. So what that means is these are above the foundation level when we're counting the stories. So the first floor starts above the foundation or at that foundation. Now under Part 9, the first floor, the foundation can actually stick out 1.5 meters. So that means the basement level could actually be raised to be up to 1.5 meters above grade for the ceiling of the basement, or that floor level. Code is very specific about that. But in terms of understanding the first floor, second floor, that becomes important when we start looking at the load tables. The other aspect about the limitations on the right-hand side here is that the roof, floor, and wall members, not membranes, members, are spaced at a maximum of 600 millimeters on center. So if you recall when I was talking about snow and the redundancy in our framing of these buildings, that becomes very important. So under Part 9, we're not allowed exceeding 600 millimeters on center. If we do, it may be possible, but it has to be engineered under Part 4. And finally, the loads, the live loads on the floors can only be up to 2.4 kPa. The tables are based on that limit. Anything beyond that, if you have a different occupancy that requires a higher load level, that also needs to be engineered under Part 4. Protection from decay. So before this section 9.23 even gets into design, it lays some ground rules, and one of them is protecting elements. As I mentioned earlier, wood joists or columns, any of those elements made out of wood need to be protected so that they don't start decaying. So anytime there is direct contact to masonry, to concrete, and basically forbid any contact with soil, because that would never be a good idea. And quite often in old buildings, we'll find sill plates that are right at ground level that have completely rotted out, and buildings are about to collapse as a result of that. So just avoid that. The next section, 923.3, leads into fasteners. And it's quite interesting that nails are the typical fastener. They are what made stick frame construction so accessible to so many. They came around the same time as the Chicago fire. And they were really a big change, because wood frame prior to that used to be big heavy timbers and traditional timber frame, traditional joinery. But the nails, now anybody could do it. You didn't need to be a craftsman as long as you could pick up a hammer. So this table, 923.3.1, specifies the nail diameters that are associated with each nail length. And why is this important? In recent years, people have been using nail guns because it's so fast on a job site, but the nail size that fits in a typical nail gun is actually a different diameter. And they're great, they're fast, they're efficient, but we want to make sure that the builders are actually using the right size nail, or that we've accounted for it. So this tells us that if you have a 57 millimeter long nail, for example, in the table, that the diameter of that nail must be 2.87 millimeters. It doesn't tell us where those need to be used. That comes in a few minutes. We'll talk about that. So the next table, 923.3.4, that's where we specify the actual nail that has to be used for specific locations. I have that tabbed in my version of the code because we seem to always need to refer to it. So this table 923.3.4, and as an example, it gives the connections between studs and the wall plates, or a rafter to a top plate, or a collar tie to a rafter. So all of these instances are covered in the table. It tells you how many nails are required and what length of nail. And so if you know the length, you can go back to that other table, 923.3.1, and determine what the diameter of the nail is. Very useful, and it's completely prescriptive. If you were to ask an engineer to determine if that capacity for that number of nails is sufficient, the answer would very likely come back no. But from historical record and the performance of these buildings, these nailing patterns seem to work just fine. So as long as you stay within the prescriptive requirements of the code, it all makes sense. There are other tables under 923.3.5 that also talk about screwing and nailing of sheathing. And this is a new addition to the National Building Code because it actually refers to wind speed and seismic behavior in different regions. So now we can actually, with a little more confidence, be able to say that yes, our plywood on the walls or plywood on the floors is nailed in accordance with the code for a certain wind or earthquake level, without overdoing it in areas that don't really have a high seismic risk or high wind potential. So I'll just show you an example here. All of this is summarized in tables A, B, and C. This is an example of table A. Table A is for the lowest case, least amount of wind, least amount of seismic. And so at the bottom of this table, second row from the bottom, say we have plywood or OSB as our sheathing element. The minimum length of fasteners, if they're common nails, would be 51 millimeters. If they're ring nails or even screws, some people, if on a floor, they'll glue and screw the floor into place to help reduce squeaking. Minimum length is only 45 millimeters. That's pretty short. Roofing nails are not allowed, and staples are allowed. So that's kind of nice because some people like to use staples. Normally on a part 4 building, structurally designed, we wouldn't expect to see staples, but under Part 9 they are acceptable. And then finally in the last column, the spacing requirements for the nails or the screws in the sheathing. And so here we see the minimum of 150 millimeters along the edges of the panel. So that means the panel of plywood. So an individual sheet of plywood along the edges of that ply have to be 150 millimeters on center. It's not along the edges of the floor or the edges of the wall. It's referring to the edges of the piece of board. And all the other, then that's just along the edges that it's 150. All the intermediate locations where we're nailing or screwing to the joists or the studs, those in the middle can be 300 millimeters on center. I have an image to show you in a second just to show that. But here's an example. That's a long corridor that completely sheathed with OSB. You can see a door opening on the right under one of the lights. But on the inset here, I've overlaid a photo where you can see a gap or a joint between two pieces of OSB and some of the nail heads, and the spacing measured out between the nail heads. It is a requirement in the code to have a small gap between the sheathing, so that's good. But you can see that there really wasn't a lot of attention paid to the spacing between the nails here. On the left panel, we only see one nail. Just point to it here. And on the right panel, we see two nails at a different spacing, and we don't really know where the next nail is down. So a little more attention to detail by the builders would have been better in this case. So here we go again, just explaining the same thing one more time, that at the edges of the panel, we expect to see the 150 millimeters on center, and that at the intermediate locations, they're at 300 on center as a maximum spacing. Okay, maximum spans, and this is where we start to look at getting into thinking about load tables. Section 923.4. So this is where we have limitations. Part 9 works provided the following. Either the floor serve as residential areas, or the uniform live loads don't exceed those for use in residential areas. And those live loads are listed in Part 4, but we're using them in Part 9. And there's a table in Part 4 for live loads. And the spans are measured horizontally, so even for sloped members. So if you have a sloped roof, and if you have the notes that were sent out a few days ago, I've added this line on the spans are measured horizontally. So if there's a sloped roof, when we're using the tables, we're still measuring horizontally. And the other thing is that when we measure, we're measuring from inside face to inside face, and that's our clear span for using the tables. If we don't meet these requirements, if we have to do things differently from that, then automatically we're thrown into Part 4 requirements, and it's an engineered design. I had a question that if the nailing in the previous photo was substandard, will the builder have to redo it? And in fact, yes. And the reason I took that photo was I was a third-party reviewer in a lawsuit over poor construction practices. So yes, they did have to go back. It isn't really that hard to do, though. They just strip away the drywall, re-nail it, and patch it up. A few more notes on maximum spans for wood joists, rafters, and beams. And this is the fun part where we get to use some of these load tables. The nice thing is the tables are now just easy to get to. Everything's in this one volume, but there's so many tables, and it's so easy to mix them up. I find you have to really be careful reading the titles of every table. So here, for your convenience, we've listed off the pages for each of the different types, because I don't even think there's an index for the tables. That would be a nice addition. So the tables A through G, these are on pages 449, or is it? Yeah, 449 to 462. So I've missed a few of them at the beginning, but those are the ones that are specific to joists and rafters. And the next group from H to K are the built-up wood and glue-laminated timber beams. And then the next group that we have here are for the design of ridge beams in a roof, so that they're all on one page on 471. And we'll go through some examples in a moment. And then there are a whole bunch of other sets of tables. And so here are the steps. So the first step, we'd go through and select which application is appropriate from the span tables. So if we're designing floor joists, table A. If it's floor joists, but they're special cases, and we'll talk about those in a moment, table B, etc. And so ceiling joists, roof rafters. So let's go through these in a little more detail. The first one, floor joist, general cases. This is just a typical joist with no special finish on that joist. Sorry, I'm through it, just to pull it open myself. We would go in and make sure that our case actually applies to that. If it doesn't, then for a floor, we would go to case B or table B. And in that case, if we have concrete topping or if we have a ceiling down below attached to the joist, then we would use table B. So if you recall when we talked about deflections earlier on, if there's a ceiling, drywall or plastered ceiling attached directly below the joist, there's a more stringent deflection criteria. So we need to consider that, and that's why there's a different table for those. And if there's concrete topping, well, there's additional dead load, and so the joists have to be able to resist that, so there's an additional table for that. Some of the other things that are considered in those tables is whether or not there's bridging. Bridging is blocks of wood that are attached between the joists at the midspan or the third points. And when you add bridging, it actually helps spread and distribute load between joists, and it helps reduce vibration, so there's a benefit to having the bridging. Ceiling joists we talked about earlier, those are for cases where you have an attic, but that people aren't accessing it and storing material in there. And so if there's no stairway to provide access to an attic, then you can use that table, unless you have other information that makes you believe it will be used for storage or other loading. And then the roof joists. So joists are referring to roof members that are essentially flat or horizontal, as opposed to a rafter, which is typically for a sloped roof. And each of those tables is broken up, kind of fine-tuned for each of the different snow load levels. So the first table is for snow loads between 1 and 2. So that's table D. So snow load of 1 kPa, 1.5 kPa, or 2 kPa. I hope you're following along. On page 455. And we'll go into more detail on the tables as well. And the roof rafters, same thing, they're set up in the same fashion. So the first tables, I'm sorry, I forgot, the table should be table D, E, F, and G, and they all say D right now. I'll have to edit that. So if we were to go to table G, that's on page 461. The roof rafters, so these are sloped rafters that could have 2.5 kPa or 3 kPa loading on them. The next step would be to select the species group. So the groups in Canada, and actually in the US as well, for the most part, we use softwood lumber in Canada, and that includes Douglas fir, hemlock, spruce, pine, and other types of fir, and this kind of catch-all category called northern species, which would include things like cedar. But the code is very specific about which species are included and which ones are not. So if somebody's telling you that they've got a lot of land and they're going to be clearing it and making their own lumber out of it, make sure it gets graded, and part of the grading they'll be able to determine what species they are. And then step 3 is grading. So we have 5 different grades that are recognized by the code. Structurally, we normally only accept number 1 and number 2, but the best grade, and these are ranked, the best grade is select structural, following that number 1 and number 2, following that number 3, then construction and standard. And sometimes, like the photo on the right here, sometimes we get a stud grade. So we'd be interested to know what that actually means, and under CSA 086 we can determine what the capacity is. Normally that type of grade would just be used for infill or non-structural applications. A little bit about that stamp. Every piece of lumber in Canada has an NLGA grade stamp on it. That's the Lumber Graders Authority. And on that stamp, on the left side, you'll see a number and some initials, and those initials are just from the sawmill and their sawmill number. What's really important as a reviewer, if you are on site, is looking at the grade of the material and the species group to make sure it's what you specified. So SPF is a blended group called spruce, pine, and fir. It's not Douglas fir. Douglas fir would say D-fir on it. It's not hem fir or hemlock. That would say hem fir. KD means that this piece of wood is kiln dried. That's not very common because there's a little more expense to making it kiln dried. The wood is put into a huge kiln and they bring the moisture content down. What's nice about it is it's a more stable member. It's already driven out most of the moisture, and there'll be less twisting of the wood. They'll have less wastage during construction. But right below that is the word stud. So if you saw this and it was one of your load-bearing walls and you had specified a number 1, it should have said number 1 where it says stud. And so you would want to reject that if it was a load-bearing wall. So once you have chosen which table to use, which species you're going to use, and by the way, the species are different regionally in Canada. In Ontario, the dominant species is SPF, spruce pine fir. In BC, you can get SPF, but you can also get really ready access to Douglas fir. And so you may see a combination of those on a site, as long as they're providing the material where you need it and the grade that you need, that's fine. Cedar in the northern species would be more common, say, for a deck framing, because people like to use cedar. It's not pressure treated, and it's just a naturally durable material. Now, we'll go through an example in the tables in just a moment. So step 4 will select the size. Step 5 will select the spacing. And finally, in the table, we're going to select the span from the table. So let's do an example. So let's say we have a 38 millimeter by 89 millimeter roof joist. So there's a lot of information here. So first of all, 38 by 89, it's such a strange number in metric. That's 1.5 inches by 3.5 inches. And that's what we call a 2x4. So historically, lumber was in inches, and the sizes were about 2 inches by 4 inches, or 2 inches by 6 inches, 2 inches by 8 inches. So the standard sizes are 4 inches, 6 inches, 8 inches, 10 inches, and 12 inches. And that's what stick frame construction is all about. And those numbers, 2x4 or 2x6, is called the nominal size. It's a name that we give to the size, but it's not actually that big. So when the conversion was made to metric, the decision was made to use the actual dimension. So that's how we have a 38 by 89 as opposed to a 50 by 100. That would have been a 2x4. So strange thing, we got stuck with it. Builders don't like it because nobody remembers these numbers. But that's how all the tables are set up, and maybe I'm getting too old and should be quiet about that because maybe the young guys are all using these dimensions at this point. So we're going to look at the maximum span for a roof joist that's a 2x4 effectively, and it's select structural grade. And what spacing? It's going to be spaced at 400 on center, which is 16 inches on center, which is standard framing. And it's going to be in a location, we don't know the location, but we were told that the specified load is 1.5 kPa. So we're going to look at a table. Here comes the table. This is table D. So if you go in the table, you'll see, and I'm going to tell you which page number this one came off. This is page 455. And on this page, we see Douglas fir is the grade on the left, and down below it is hem-fir. And the flip side of that same page is spruce and then the northern species. So that's where you can select off the grade of the species that you're going to be building with. So if I'm in Ontario, I'm pretty certain that most of my builders will want to be using spruce. So that'll be on the next page over. But for this example, let's assume we're using Douglas fir. So I'm somewhere in British Columbia or Alberta. I have good access to Douglas fir, and I'm going to use select structural, and nobody's going to complain because I've chosen the best product that's out there. And that would be the ideal world. The next thing we look at is the joist size in the table. So we're saying we're going to use a 38 by 89. And now I can look at the snow load. So my snow load is 1.5 kPa. And the spacing of the joists in the question told us to look for a 400 on center spacing. And from that, I now have the span, which is 2.15 meters. So I know that on a roof joist, I can span 2.15 meters with the 38 by 89 select structural Douglas fir with a specified snow load of 1.5 kPa. That is not normally how you'd use the table. You'd probably be saying, you know what, I have a span of 4 meters. What is the size of the member that I need to use? So then we would go in here and we'd say, well, I'd like to space them at 400 on center because that's an industry convention for spacing. Am I able to make something work with that for that span? And if I needed 4 meters, the first one that's greater than 4 meters is here, and if I come across, it's a 38 by 184. So all other factors being the same snow load, same species, same grade, 38 by 184 will work for my 4 meter span. A 38 by 184, that's a 2 by 8. So the tables are set up, they're very repetitive. First one is a 2 by 4, the next is a 2 by 6, 2 by 8, 2 by 10, and 2 by 12. Tables don't go beyond that. They don't have any wider members. This is what you get. And on mine, I pencil in next to it those dimensions in imperial. On some of our jobs, we're designing in metric, and others we're doing imperial. The worst case scenario is to design it one way and have somebody come back and ask you to convert to the other dimensions and make sure that you have all the millimeters correct. So I'm just going to back up. Somebody has asked just to see what the slide says. So just to repeat, we were looking at the maximum span for a 38 by 89 select structural roof joist. And the joists are spaced at 400 on center. Now, I did have another question earlier regarding bridging, and what was the definition and the use and the need for bridging. I didn't scan in the table, but if we go to floor joists, so if you have table A available, that's on page 449. Give me a second to find it. On 449, we have floor joists. The format of the table is the same as the one I just showed, where the species is on the left. This is the previous one for the roof. Species is on the left. The grade is the next column. The size of the joist is the third column. But now, instead of snow loads, these are specifically for floor joists. So we're not given an option about load because the tables have been calibrated for the Part 9 floor loads. And we are given options for joist spacing with or without bridging. And the bridging If you recall, it refers to blocking that's put between joists and used to help control vibration and improve the distribution of loads between joists. So if you compare the bridged case to the non-bridged case, you get a little extra span when there's bridging. And another question I had was, is the span face to face of the supports? And the answer is yes. Span is the clear span, and it's the horizontal distance. If it's on a rafter that's sloped, it's actually the projected horizontal distance between supports, face to face of the supporting members. Supporting members could be a column or a beam or a wall. So, as I mentioned, there are these special cases for floor joists. So if we go to page 9-451, so on this is table 9.23.4.2-B. This is the special case where either we have ceiling underneath that's attached directly to the joists, or we have additional concrete topping on the floor. And that topping adds weight, and there are limits to how thick and how heavy that concrete topping can be. But the purpose of the topping is to help reduce some of the vibration concerns. It adds mass, and so when you walk on a floor that has topping, it just feels a lot more solid. Sometimes people run heating cables within the concrete as well. I had a question about I-joists as well. Can wood I-joists, which are an engineered product, be used under Part 9? So it's a kind of gray zone because as a product, the I-joists actually fall under Part 4, but a lot of Part 9 buildings have I-joists in them, but they're expected to be an engineered product. So the supplier would provide engineering, or the lumberyard that they're ordered from, and the product suppliers for I-joists would have their own version of load tables and span tables outside of the Part 9 span tables. And actually, as a product, the I-joists are quite nice because they will rate the capacity by including the effects of the sheathing, either plywood or OSB, and whether or not concrete topping has been added, and what the nailing or screwing pattern is, or whether the sheathing is glued or not glued. So there are a lot of other variables in designing I-joists. There are some tables as well specific to I-beams. So if you go to table 923.4.3, just find it here, and that's on, sorry, that's back in the code and not in the load tables. So that's back on page 9-134. There's a table for I-beams. So occasionally we need to have steel beams in a building. That may be primarily wood, but for whatever reason, based on the spans or availability, an I-beam makes more sense. And so I've drawn here on the bottom right an orange box, which is just representative of the location of an I-beam that may be supporting a single floor. If there was a wall that was above that I-beam, continuous up to the roof, then it would be supporting 2 stories potentially, or if that I-beam was actually down in the basement, it would be supporting potentially 2 stories. So the table is set up to allow for up to 2 stories support. And if you read carefully, and that's the trick with all of these tables, there are so many assumptions built into them to make them work. The supported joist length is the first criteria here, and that's equal to half the sum of the span of the joists on both sides of the beam. So the beam is the orange element, the joists are in the floor, and what we're asked for here is what, as an engineer, what we call the tributary width. So that's the area of the floor that's supported by the beam. So in this case, it's half of the total width of the building. So say it's 4.2 meters, and we are supporting one floor. The maximum span, so the result from this table gives us the maximum span, and say we needed to span at least 5 meters, this second element here, the W200 by 21, is good for 5.7 meters, so it exceeds the requirement, then that's the one we want. We want to be able to span at least 5 meters for my example. And then we would design columns to support those beams. Now, back to some of the wood framing. There are restrictions on cutting holes and notching members. And this is probably the most frustrating thing about wood framing is the framers will come in and build a really beautiful structure, and then the next trades through are the electricians and the plumbers, and they will cut and notch everywhere with generally no regard to what they're doing to the structure, just based on my experience. So there are rules, and here they are. So holes drilled in roof, floor, and ceiling framing members are not allowed to be greater than 1/4 the depth of the member, and must be located not less than 50 millimeters from the edges. And I've got an image to show you in a second. So this is spelling it out, and it's also saying if it doesn't meet those requirements, say you need to have a 3-inch diameter hole, but it would exceed one of these rules, then the only option available to you is to make the member bigger. There's not much else you can do. So here on the next slide, you see some holes. And here we have 2 hole sizes shown. The larger of the 2 holes is the governing size, and that's the one that we use to check the depth. That makes sure that it doesn't exceed the 1/4 of the total depth of the member. And the rule about 50 millimeters from the edges. So the top zone and the bottom zone are no drill zones. One other thing, rule of thumb, if you can't remember this, generally speaking, and not always the case, but generally, keep the holes in the middle 1/3 of the depth and the middle 1/3 of the beam, of the length of the beam. So middle 1/3, middle 1/3. And that's generally the rule that's used for I-joists, and it generally, I'll say, applies to wood frame as well. Down here at the bottom, I have a list here. So for an example, a 2x6, which is the second item, the maximum hole size is 35 millimeters, or 1 3/8 of an inch. In a 2x4, the smallest size, it's too small to even permit a hole. So you wouldn't want to be using those on a floor if you expect it would be pretty hard to make a 2x4 floor work anyway. So if you're expecting holes, definitely go with deeper members. Bulkheads is always an option to avoid holes, but most architects I know do not like bulkheads. 923.5 talks about notches. So we just talked about holes, but what about a notch? Say we do want to make a cut near the top of a beam or near the bottom. Well, generally they're not permitted, but if the notch is on the top and very close to a support, then we are permitted to have a notch, but it has to be within a half of the joist depth away from the support. I'll show you that in an image. And it has to be not deeper than 1/3 of the joist depth. So, and again, just like drilling holes, if you really need that notch, then increasing the depth of the member is the better option. Difficult to do once something's already been built. But here we go, this is what's meant by that. So the depth of the notch, the height of it, is 1/3 maximum. 1/3 of the depth, and the distance from the support is this limiting distance, which is half the depth of the beam, or the joist over. No notches permitted on the bottom. No notches permitted on the top, even at the middle or any other locations. This is the limitation. And so we have a table here listing that off. And I'm just reading a whole bunch of questions. Can I repeat the steel beam table example? So I'm going back, I'm sorry. Here we go. Steel beam. So we have a steel beam that's picking up a single floor. The contributing load comes from the floor, the floor joists, which span from the wall to the beam, and again from the beam to the other wall. So the weight supported by that beam is half of the distance. So say this is 8 meters across, so half that distance is 4 meters. And we go to the table and we say, okay, we're going to support approximately 4 meters, so 4.2, and we're supporting a single story. We go down the table and we determine for each type of beam what the maximum span is. So if I know that I want to, it works out that my columns can be spaced at 5 meters on center in the building. I want to have a beam that can go at least 5 meters in span. So the first one, as I go down the table, that is at least 5 meters, is this one with 5.7 meters. I read across the table, and it's a W200 by 21. These are metric numbers. The 200 is the depth, so 200 millimeters deep, which is 8 inches. And the 21 is the weight of the beam. The lower the number, the less steel, the less cost. So you can see the next one up, it's also a 200, but it's a bit heavier. It's a 27, and the next one's a 31. And the heavier beams get a longer span. Question of, does this hole drill and framing apply to I-joists? So again, you'd have to look at the manufacturer's product literature to see where the holes can be made. Generally, it's the middle third of the length and the middle third of the depth, but they do have hole charts in them. Regarding notches in I-joist, not allowed. There are some limitations on that because the flange that's where the capacity really is. And again, their product manuals would have a lot of that information. The question about unless the depth of the member is increased. So if you can't meet the requirements for the drills or drilled holes or for notches, try to increase the member to a deeper size and then check if that size will accommodate the hole and notches that you require. This assumes that you're taking care of this on paper in your design office before it's actually built. Because if it's already been built, then increasing the size or the depth of the member usually is not an option. Can rafters be bird's mouth cut is another question, and the answer is yes, the code does allow for that. Okay, I'm going to keep moving along here so that we can finish up, and then I'll address a number of other questions that have been coming in. Notching and drilling of studs and top plates and roof trusses. So, wall studs, in general, they're not to be notched or drilled or otherwise weakened unless they're reinforced or if the notching or drilling is allowed for in the design. So if you have 2x4 wall studs with huge holes or notches in them, generally the answer is no, they will have to be replaced. Same thing with top plates. Top plates are the horizontal piece at the top of a stud wall before the next floor is attached, and those are required to be continuous elements, or spliced where required, but cutting or notching a top plate will compromise the capacity of the top plate. There are instances where they can be allowed, but in general, no. Roof trusses, if they're prefabricated wood trusses, that's an engineered product that falls outside of Part 9, and no modification is allowed to roof trusses if they're prefabricated. They have steel truss plates on them, and any modification has to go by the manufacturer's engineer first. Sometimes they do get damaged on job sites, so there'll be repair detail that's required, but intentionally going and notching them is a no-no. Anchorage of building frames. So building frames or buildings must be anchored to the foundation. This is 923.6. There was a hurricane in the 1980s in Florida that the winds were so strong it ripped the roofs off a few buildings, but it also knocked buildings off of their foundations, and that's when they realized that not everybody was putting anchor bolts in the foundations to connect the wall structures down to the foundations, and so a lot of damage could have been avoided if they'd connected them. So there are a couple of methods that are approved under Part 9, and one is to embed joists directly into the concrete, and another is to fasten the sill plate to the foundation of the building using 12.7 millimeter anchor bolts, that's half-inch diameter anchor bolts, with nuts and washers, and that they're spaced no more than 2.4 meters on center. Why do we specify nuts and washers? Because they're useless if we don't actually have the nut and washer on them, and that is a big concern. And here's a photo from one of my inspections where this was a final framing inspection, and a whole bunch of the anchor bolts they'd just forgotten to come in and put in the one on the left is missing a nut and a washer. The one on the right is missing the washer. So that's a requirement. And here's an example graphically explaining what I just said as well. The upper image shows that the first floor joists are connected right into the foundation wall. Not my favorite detail because I wonder about the actual connection. And again, we're putting wood in direct contact with masonry or concrete, but it is permitted. And then the bottom one showing the anchor bolts, which extend down into the foundation wall. These anchor bolts, code requires them at 2.4 meters on center, that's 8 feet. Typically an engineer design would be about half that length, so if you can make it work under Part 9, you'd have half the anchor bolts and still meet code. 923.6, anchorage of columns. So that earlier column I showed you had a column cap and a column base, and that was a method of connecting the column down to the foundation as well as up to the beam above. And without those connections, a building would be susceptible to uplift. So think of an entrance canopy on a building that may have 2 columns near the where the people approach the building, and then as you get to the building, the rest of the canopy is attached to the building. Well, those 2 columns at the front, if a wind gust comes along and lifts up the canopy, and there's no proper connection between the canopy and the canopy will actually fly away, and that has happened on buildings. So we look to make sure that columns are connected, and again, the lateral movement by connecting the top of the column to a structure above prevents the column from moving around and becoming unstable. Sill plates, 923.7. So these are the horizontal wood plate that the stud walls bear upon. So sill plates must be at least 38 by 89 millimeters, and they typically match the sill plate to the size of the stud. Not always, but they have to be at least the same as the stud. So a 2x4 wall, which is 38 by 89, that's the minimum stud size. The sill plate would be 38 by 89. Does not leave a lot of room for anchor bolts, particularly if the foundation has rebar in it, and when they drill down to put the anchor bolt in, they hit a piece of rebar. There's not a lot of wiggle room. So a 2x6 sill plate is a lot more forgiving. There's just enough extra room there. When they put the sill plates down, they have to be leveled, and that can be done by shimming them and then packing non-shrink grout underneath to level it out. Or if the foundation is actually level, then it can just be put straight down onto the foundation wall. Definitely polyethylene or gasket could be put down first, and then the sill plate on top to provide that moisture separation. Beams and support floors, 923.8, the connection of beams to the supporting floors. In this case, we talked about having the support being as wide as the built-up beam itself, but we didn't talk about the depth in the other direction, and that's shown as this 1 with a circle, that dimension. That dimension has to be at least 89 millimeters, which is 3.5 inches. And and that's for beams it supports. For bearing of built-up wood beams, there's a table 8A, A8 to 811, provide additional information for you on the bearing lengths. These bearing lengths can also be designed by an engineer, but Part 9 does give you the minimum requirements. And built-up wood beams, they have to be, just like we talked about built-up posts earlier, built-up beams can be nailed together or bolted together out of individual pieces of 38 millimeter stick frame material, and the rules for nailing those are also prescribed. Floor joists have to have at least 38 millimeters of bearing, except when they're supported on ribbon boards. So what's a ribbon board? This image shows a combination of platform framing and balloon framing all in one image. On the left side, we have platform. So we have the joists sitting on top of a wall. The bearing area, the bearing support is 38 millimeters on top of that double top plate. So here, this is the double top plate, and there's some nails that are shown. Those nails are specified in that table that I told you that I always have tabbed, table 923.3.4. That gives the nails. And then on the right-hand side, we have the balloon frame. So this is a case where the stud is continuous, multi-stories, and the floor joists sit on what's known as a ribbon board. Some people call it a ledger. They cut the stud, they notch the stud, and they insert this continuous board, and so the floor joist sits on it. But we also nail the joist to the stud, so it's the bearing is taken by the ribbon board and shared a little bit by the nails, and they provide some additional stability as well. (923.9) Floor joists, they can be supported on beams or framed into the side of beams for a depth of at least 38 millimeters. So the floor joists also have to have a bearing. These days it's more common that the bearing would be provided by a light gauge metal hanger, face-mounted hangers, or top-mounted hangers. Those are probably the most common. There's also this requirement that bottoms of floor joists must be restrained from twisting at each end by toe-nailing or bridging. So we don't want floor joists to twist around. An rim joist will also prevent joists from moving. But in a situation like this, shown in the center image on the balloon frame, we'd expect to have some sort of bridging at the support to prevent any rocking over of the joists. They don't just fall or twist over. I'm going to skip through a few of these slides pretty quickly. Header joists, if we do have an opening in the floor, there are requirements of whether or not these need to be single or double headers, depending on the length of them. And the two joists on the side of this opening are called trimmers. So there's also a requirement for those trimmers to be doubled if the span of the opening is more than 800 millimeters. Just have a few more slides here. Wall studs and spacings are also provided in table 923.10.1, and they must be placed at right angles to the face of the wall, so they're not allowed to be skewed. The bottom image here, it would be very rare to see a stud installed in the weak direction like this. Normally, we have a bigger cavity. And studs must be continuous for the height of the story. You are not allowed to splice studs partway up a wall. That would be creating a pin. So this is an image of a single story that for whatever reason has been designed as a knee wall and then some sort of floor joist going the other way and then studs continuing up above. This is prone to buckling out, so not a good situation. So the studs need to be continuous from the floor up to the ceiling. And wall plates must be not less than 38 millimeters thick and not less than the width of the wall. So the top and bottom plates have to be the same as the studs or greater. And bottom plates must always be provided. Wall plates, at least 2 top plates are provided in load-bearing walls, and the reason is that we want to be able to have continuity at the top of the wall. The joists on the plates must be staggered if they're sitting on top. So here's an example with a continuous wall plate at the top. It's a double plate. Of course, lumber has a finite length, so at some point in a long wall, we need to splice the top plates, so there are rules about the joint spacings for that. And also at the edges or the corners of walls where 2 walls intersect, there would also be a splice as the top plates lap over each other. Framing over openings, basically any opening that's more than the space between studs, so more than, say, 400 millimeters on center, is considered an opening in a structural wall, in a load-bearing wall. And that would require a lintel overhead to bridge over the opening. In a non-load-bearing wall, they must be framed with 2-by material of the same size as the studs. And part of that also requires a double element for fire separations around openings in a fire separation wall. So as I just mentioned, in a load-bearing wall, if the opening is more than the stud spacing, they must have a lintel above. And if 2 or more pieces are used as a lintel, say you have 2 2x8s over an opening, the 2 2x8s have to be nailed together. I'm going to just skip through a few of these slides. Just so you're aware, the newest version of the building code, the 2015 code, added a section 923.13 related to bracing for lateral loads from wind and earthquakes. Engineers are happy about that. You may not be. Roof and ceiling framing, roof rafters and joists have to be continuous. We're not allowed splicing those. Roof and ceiling framing must be supported at the ridge. And there's a ridge span table, as we discussed earlier, 923.42-L, with all the span tables for ridge beams. Subflooring is specified in clause 923.15. Minimum thicknesses for the subfloor are specified. Roof sheathing, lumber sheathing or panel sheathing must be installed before the roofing material, and those are specified in 923.16. Similarly, wall sheathing is required. This is my final slide. And the tables for wall sheathing are in 923.17. And so that just basically specifies the most common sheathing elements, which these days are plywood and OSB, pretty much used interchangeably. So that's the last of my slides. So I'd like to just move on to answering a few questions if people are still willing to stay here. And just realize the time. One of the questions I had was, what's the most commonly used or preferred method of anchorage? So the anchorage, we talked about anchor bolts. Just move back here. Anchor bolts can be cast in place in advance. They're steel bolts. Here we go. They're J-bolts. So if they're cast in place, they're usually about 2 or 3 inches on the hook and between 6 and 12 inches long, depending on the need. And they can be left in the formwork before the concrete's poured, assuming that they don't shift around and the contractor does a good job. Quite often they don't. So to give them more flexibility, products like Hilti and other similar anchors that are epoxied into place can provide similar resistance. Companies like Mytech and Simpson provide a cast-in-place strap, which we've seen on job sites that can be put in place and then nailed on the sides of the studs. It's another method of installation. That combined with joists, with anchor bolts. So those are probably the most typical methods. Here's a question that says, does the lintel have to be placed below the double top plate? Or can it be placed where it sits, it splits the continuous double top plate? So no, the answer is the lintel has to be below the top plate. So let's have a look at an example of wall. So in this image of a wall, if we had to remove one of these studs, the lintel would be, say, a double 2x6 would be placed between these studs, and there'd be a jack stud below it on each side, and these would be the king studs on either side. And that would bridge over. Is there a clause in the NBC which specified what building types can be designed and built without input from consultants? That's a good question. My understanding, and I may not have the answer to this, but my understanding was that Part 9 was designed so that anybody should be able to read it, and with the approval of the authority having jurisdiction for that region, they would be able to build as long as they followed those requirements. So they'd still have to go through the permit process, and it may be at that point that they would be directed or steered to speak to an architect. Or in Ontario, we have people who are called BCIN, Building Code Identification Number. They've taken exams and can guide them through that process. So I know as practitioners, it's not our favorite thing to see, but I believe that that's the intent. A question about what is framing around the windows. We didn't get into that, but basically any opening, whether it's a doorway or a window, does require framing, and that is specified in section 923. Which is framing over openings, page 9143. So here we have framing over openings. First section is in non-load-bearing walls. Then the second section is in load-bearing walls, and so there's it's defined with the size of the lintels, and those lintels are also specified in tables. So there are span tables for the lintels over openings, and in addition to the requirement for the jack studs and the king studs to support those lintels. Next question says, the fastener table provides the length of the screw, but not the diameter of the screw. That's a good question. I know under CSA 086 standard, the screws for wood screws are defined, and so because the National Building Code does point people towards that, I would guess that we should probably look at CSA 086 to confirm the screw diameter if it's not specified here, and I agree, I don't see it there. This is a new table for the 2015 version. The minimum spacing requirement between panels of OSB or plywood, where can this be found? Again, I know it exists under CSA 086 for the wood design standard, and it may not be specifically mentioned in Part 9. The fact that they've even added this table for the nailing and screwing requirements, that's all new. So probably they wouldn't want to reproduce everything from the other code. But I would say, I would point you towards that standard. Now, there are a couple of questions that just came in that I don't actually understand the intent of the question, so perhaps the person who asked them. When do we use the attribution tables? I don't know what that's referring to exactly. And the next question is there a code reference for an exclusion for the 12 millimeter threshold required for accessibility, as it conflicts with the 150 millimeter requirement grade between wood and grade? Well, the requirement for the 150 millimeters to raise the foundations above the grade is for the typical foundation requirement, but at entrances and doorways, that would have to be waived so that people can enter the building. But as I understand it, the reason for raising the foundation at those locations is to protect the structure above. And since this would just be a doorway for accessibility, I can't see that that requirement would need to be kept. Okay, sorry. So I thank you for the follow-up to the question. The question was, when would the attribution tables be required? The attribution tables are the ones that start on page 263. So these are objective and functional statements. This is a prescriptive section of the code. However, our code has now been converted to one that allows for people to provide substantiation if they want to deviate from what's specified in the code and they want to provide an alternative solution or an alternative method of construction. They can do so provided that they meet these functional and objective requirements of the code. So for example, if I said I don't want to install anchor bolts in my building, then I would have to find the appropriate clause here in the attribution tables and defend my proposed alternative solution, which may be nailing straps. I'm not quite sure. Something that provides the same level of performance for the code, and then defend that to the authority having jurisdiction, so a city building department or chief building official. And that's the purpose of those. So, you know, if I went in here and found 923.6.3, which is on page 318, you don't need to look this up. It does refer me to the functional and objective statements for the reason that those anchorages are required. Question regarding what is the specification for fasteners and the anchors. The code just provides the diameter of the anchors, I believe. And at some point, I do recall seeing the length of the anchors. Following question, what is the meaning of 1 in 50 HWP? That's a specific question to one of these new tables, and particularly the one for sheathing. HWP stands for hourly wind pressure, and this was added to the current code. Normally, we don't refer to it as that, but that's the way they've chosen to list it here in the code. And 1 in 50 is the return period on that level of wind. So if we go back to the climatic tables, and I'll just jump back. Let's see here. So here are the climate values for different cities. Next to the snow, where the red arrow is at the top, there are the hourly wind pressures. There's 1 in 10. We don't want that. Next to it is the 1 in 50. So there's the hourly wind pressure. So if I pick, this is a page out of the Ontario section. If I pick Thunder Bay, the hourly wind pressure is 0.39 kPa. And so I would be able to use the lowest value of wind in those tables. I believe that the first criteria is 0.8 for the hourly wind pressure. Similarly, if I was concerned about seismic design, on the right-hand side in the same table, we have SA, which is the spectral acceleration at the 2 seconds. So 2.0, it requires 0.2 seconds, so 0.2 seconds spectral acceleration. We go down that table for Thunder Bay, and we have 0.095. And so, same table A on page 131, that table would apply for Thunder Bay. So then I'd be able to go in and determine the fastener spacing and length. Were there any more questions, or did I miss any? And I think we're done, so I thank you very much. And I just want to say, if you have any questions or follow-up, please feel free to get in touch with the organizers, and we'll do our best to answer your questions.
Are you single?
And yes, if you do want to contact me directly, that's fine as well.
That's terrible. He really doesn't know the dumbest shit. He's already grabbed that so much.
Thanks. Have a great afternoon and evening wherever you are.
Thank you.